Hello and welcome to this lecture about network security systems. In this lecture, I'm going to describe some common network security systems or functions that can be used to um, mitigate some attacks, detect and mitigate some common security attacks. All right, let's start. These are the references. And before I'm talking about the network security systems, I want to go back and discuss something that I mentioned before in the lecture, the firewall lecture. So, one of the most common application appliances, network security appliances, is called firewalls or unified threat management systems, or sometimes we hear the term next generation firewalls. These are appliances. By appliance I mean either a hardware piece or a virtual machine that does um, multiple functions. And one of those functions is packet filtering, which we talked about. But there are also some other functions that are packaged within one device, and this is what we call unified threat management or next generation firewall. So some of these functions that are packaged are anti-spam filters, application filters, intrusion detection, intrusion prevention systems, virtual private networks, web filtering, SSL inspection, deep inspection, sometimes we call it malware detection. All of these sometimes they're packaged together and put in a system that we call firewall. Right? In fact, it's not just one function but multiple functions. So the main purpose of this lecture is actually take some of these functions and others and look at them closely and see what they do, how they do it, and where they can be deployed in the network. Because they can be deployed as individual systems as well, and some of them often do. Okay, let's take a look at some of the definitions. Some of them have been visited before. The first thing that I'm going to talk about is the term anomaly. When the term anomaly is used in the networking context, usually we refer to unusual behavior in the network. So in this picture, for example, you see the traffic that goes, or not necessarily traffic, it could be the free memory or the CPU usage, any kind of metric that we are monitoring and recording. But at some point, we see something unusual happening. In this case, the spike here in this graph. This is what we usually refer to as anomaly, which is something unusual. In this case, in this particular case, the anomaly is related to the volume or the metric itself. If this is a CPU usage, we see that the CPU usage all of a sudden spiked for some reason. But if you are talking about, let's say we are monitoring the bandwidth or utilization on the internet connection of the network. And the internet connection often has predictable pattern, right? Let's say we are monitoring the bandwidth, and the bandwidth is moving up and down. Maybe during the day, between 8 o'clock and 5 o'clock, the bandwidth increases, and when during off-hour time, the bandwidth is low, right? This is the regular pattern. If we see a spike at some point, we'll see unusual behavior that we consider an anomaly, because on average, the traffic the utilization doesn't go up that high. So this is what we mean by anomaly when it comes to traffic volume, or when we measure any metric in the network. Anomalies can be a symptom of a new or never seen before attack, or even seen before attack. So for example, let's say there is a denial of service attack. There are multiple ways for denial of service attack to be performed, but one of them is increasing, or the symptom of that is increasing bandwidth going, or increasing the amount of traffic going to a server. We can see that as a spike in the traffic. Other types of anomalies, not necessarily related to traffic, but let's say usually we see few pings going on in the network, and all of a sudden we see a ping that goes to the entire devices in the network. So the network is being scanned, right? Every device or every address available in the network is being pinged. So that could be considered an anomaly as well. Unusual traffic going to a specific server, or unusual traffic coming from a specific device that's it's not typical, right? A ping coming from a camera. Well, a camera doesn't ping usually, right? But a ping coming from a camera may indicate that somebody hacked into that camera and started sending ICMP packets. So all of these can be considered an anomaly or something out of the norm in the network. One of the things that network security aims at is to detect these anomalies so that we can figure out the reason and prevent the cause if it's an attack. Another term is called exploit here. Exploit is sometimes known attacks. We know there is a weakness in the operating system, a weakness in a device, and somebody is trying to exploit that weakness. So the term that I used here, or the term that you see in the slide, is a zero-day attack. So what is the zero-day attack? If we know all the possible attacks out there, we can basically build defenses against them. So I know that somebody is trying to attack port 8080 in the server. Okay, I'll close port 8080. If there is a vulnerability in the operating system, I may upgrade it. If I know there is a particular virus, I may have an antivirus for it. So all of these can be known attacks that we can plan ahead to defend against them. The zero-day attack is an attack that we didn't know before, or exploits a problem or vulnerability that we didn't know before. So from the security perspective, that's an attack that we had 0 day to plan for, or 0 day to prevent. It's a surprise. And some of the systems that I'm going to talk about today they are designed to exactly to mitigate the 0 day attacks. Right? So these are the things that we're going to consider. Some others, they are not related to this. Some other systems, they are for other purposes, but we're going to talk about few systems that are designed for mitigating 0 day attacks. Another definition that I want to talk about is denial of service or denial of service attack. These are attacks designed to attack the availability of systems, and they can use any protocol, whether it's TCP, UDP, or any other ICMP. There are 4 types of anomalies that may be an indication of denial of service attack. So I already explained the high volume, right? So you see unexpected high volume of traffic, it may be an indication of denial of service attack. Not necessarily all the time. It could be just simply the organization is trying to back up large volume of data, or there is an event going on, so there are more people using the network. So there are legitimate reasons for having something unusual in the network, but there are also some indication, or it could be an indication of an attack. Another example that I mentioned is when you see a sweep or scan attempts. So there are ICMP ping or CMP echo messages going all over the network. So somebody is trying to discover what device is out there. Or somebody is going and trying to connect to every port available in a server, going to port 80, 81, 82, trying to discover what open ports are out there. So maybe the attacker tried to exploit them. So that's another anomaly that may indicate a denial of service attack. A large volume of traffic originated from a single IP, or vice versa, large volume of traffic destined for a single IP. Sometimes the volume of traffic is not general volume, but volume of particular protocol, right? So we expect UDP to be a certain percentage of the protocol in the network, and all of a sudden it surges to much larger percentage of the traffic, right? Or SNMP traffic, which is used for network management and monitoring, we see it maybe it should be low compared to other levels of traffic in the network, and all of a sudden we see that went up significantly higher. So these are large volume or high volume of traffic of particular protocol that's unusual, right? So all of these anomalies, they can be detected only if we know the normal. If we don't know the normal, if somebody comes into a network and looks at the traffic while there is an attack going on, but there is no basis for comparison, right? So there is nothing that I can compare with. How do I know it's an anomaly? So detecting an anomaly is based largely on knowing the baseline, knowing what is the normal traffic behavior. So to be able to detect these anomalies, we need to keep track of the network behavior for a reasonable amount of time to be able to know what's normal, what's abnormal. And then we will be able to set some threshold to say, okay, so if the traffic goes up beyond this level, so maybe this is something that we need to look at. Or sometimes we need to look at if the traffic goes below a certain level. Also, that's constitute an anomaly. Why all of a sudden I don't see traffic coming from this particular device? Maybe it's shut down, right? So we can do that by setting thresholds. And that also emphasizes how important network monitoring is, right? So besides security, we need to have proper network management and monitoring as well. Another type of denial of service attack happens by exploiting some behavior of protocols. We know that, for example, one of the common ways to launch an attack against a server is by using the SYN flood attack. How does it work? Well, TCP needs three-way handshake. And the handshake starts by the client sending SYN message, and then the server immediately sends a SYN acknowledge, right? So it sends its own SYN and acknowledges the SYN that it received. And then the client will send a final acknowledgement, and then by that time the TCP session starts. Every time a server establishes a session with a client, it has to keep track of that client. It has to reserve some memory, track all the sequence numbers coming, track the windows. So maybe creates a buffer for all the packets coming. So it deals with so it has to track every client. Tracking every client requires memory. So servers usually they will have finite number of clients that they can deal with at any given time. Maybe 10, maybe 100, maybe 1,000, but there is always finite. So a common attack is the client, malicious client will send SYN, the first SYN, the server will send SYN acknowledge, and then the client never finish the final acknowledge. So now we have a partial open or half open connection where the server is waiting for the client and probably reserving memory for it, but the client never finish. And from the same, maybe from the same client or multiple clients will keep opening TCP sessions, but they never complete them. So eventually the server runs out of memory, runs out of number of clients that it can handle. So if a legitimate client tries to establish a connection, the legitimate clients will not be able to do so. Okay, so that's a common type of denial of service attack. Another type of denial of service attack happens by attempting to crash the server by exploiting some software vulnerability there. So one of those common attacks is buffer overflow. The buffer in this case is a memory that's reserved for a specific purpose by an application running on the server. And if the attacker managed to exceed that memory, right? So what happens when you exceed the memory? The whatever data you are putting in that memory, it will flood another part of the memory that was not supposed to take that data. And the attackers, by using clever methods, they can actually either crash the server altogether or actually manage to execute some commands by exploiting the buffer overflow. There are several types of buffer overflow attacks. One of them is the stack-based, heap-based, or just simply changing the format of a string, right? So a stack-based, in any application, if the application calls a function, one of the methods or the common method to call that function and pass arguments to it is by putting the arguments or the parameters that I want to send to the function inside the stack. And also the return address will be pushed into the stack itself. The stack always have a limited memory, limited size. It's not infinite. Memory is not infinite. But the attacker can maliciously put one of those arguments, one of those parameters that needs to be passed to the function, make it huge to the point that the stack will actually exceed its limit. And flows over, or the data flows over outside of the limits of the stack, and the return overwrites the return address so that the function will never be able to come back to where it to the whatever it was wherever it was called from. And it's either the server crashes, the application crashes, or the attacker can control or make something executed, a command executed outside of the stack, so it can launch another attack or launch another application. Similar to that, heap-based buffer is if you reserve a certain amount of memory to an array, for example, and then the attacker managed to use or exceed that size of the array or exceed that size of memory, it may force the application to stop working, crashes. Another type is, let's say, the application expecting a string that represents a name of user or some any other data. The attacker managed to put a command instead, right? Using special characters, using anything that's not really the expected input. Um, if the application is not written well, it instead of having that data being saved in a database, it's actually the command is getting executed and it's causing problem in the application. So all of these are um, considered buffer flow attacks. The symptoms of that, so all of that happens in the server, but from the network perspective, how do we see the signs of the buffer flow attacks? We can see it by seeing, for example, in the network, we see traffic HTTP requests with large bodies. So HTTP requests usually small, and they use a specific format. Or if you are asking to visit a website, you are going to send an HTTP request with um, a command like get, for example, or set, right? And you will see that the actual body itself for the request is huge, which maybe the server is not designed to handle such a huge request. Illegal host names. So host names they have a certain formats. If the attacker manages to have something that's not proper formatted, it may actually be an indication of trying to cause one of those buffer flow attacks. Uh, Non-existing HTTP versions. HTTP versions have specific versions that the server can handle. If you send an HTTP request with a version that's not supported, it may actually cause the server to behave in unexpected way. And finally, something that there's certain request methods known for HTTP, as I said, get, set, something like that. And if you send something like trace or connect, which are not recognized HTTP requests, the server may not be able to handle it. This all, I'll go back to say that these all vulnerabilities that can exist in the software. Now, what I mean by vulnerability is maybe the software was not written properly to sanitize the input. So if you are expecting the user to input a name, the developer should make sure that the name is actually proper characters, no special characters, no numbers, no special commands. So it needs to sanitize the input. If the developer fails to do that, then now you're creating an opportunity for the hacker to do that. So there is always a struggle between the developer writing the proper code and the attacker is trying to find something that the developers missed, right? In the software so that they can exploit it. So these are the exploits. The vulnerabilities are the things that missed in the design of the software, and the exploits are taking advantage of those vulnerabilities. Okay, so how is that related to the systems that I want to talk about? So one of those systems that are designed to detect the anomalies and alert when they see these anomalies is what's called intrusion detection systems and also intrusion prevention systems. So let's talk about the first one, intrusion detection systems. These are designed to detect unauthorized use of or attack upon a computer network or telecommunications infrastructure. The basic intent of the IDS system is to spot something suspicious and alert, or in case of the intrusion prevention system, try to actually do mitigation. But now we're going to focus only on the IDS, which the IDS does alert commonly. It just alerts the administrator that there is something not proper there, right? So the IDS tools look for abnormal data patterns that may indicate questionable action or event. And flag them. Right. There are two or three common components for the IDS: sensors, analyzers, and administrator interfaces. All right. So what are the sensors? Imagine you are doing packet sniffing. You are monitoring a network segment and reading all the packets that pass through that network segment, right? So that's what we mean by the sensor. It's a packet sniffer. The analyzer is the part where it takes those packets and look at them, either the pattern either inside or just generally speaking traffic volumes, and say, well, what is normal and what is not normal. And finally, the administrator interface is what allows the administrator to log into that IDS and try to configure it. So these are the three components. Generally speaking, they may be on the same spot, they may be the same device, but if you want to generalize, you can say, well, the sensors can be in different pieces or in different locations, and the analyzers in another location. So you can put sensors different ways in different locations, and then they send their data to the analyzer. Um, the common thing that we're going to talk about today is this is all one device, whether it's a virtual machine or actual hardware that does all or has all three components together, right? And these are the common types. IDS comes in two flavors, two types. It's either network-based or host-based. So the host-based system, from the name, it is installed on a system. So here is an example of a network segment, and the network segment has multiple devices, hosts, servers, and I can put the home IDS in the server itself. In this case, the function of the system is to monitor traffic in and out of the server and look for any suspicious activities. But the device here or the software here will not be able to look at anything else. It will be just concentrated on looking at the traffic in and out of one single system, right? On the other hand, the network IDS will, if I put a network IDS here, and it will sniff all the traffic in the segment, then it will be able to look at the entire traffic. So I'm going to put the IDS here on the network segment, and I will be able to see all the traffic going in and out of or passing through the network segment, and I'll be able to analyze the traffic there. Okay, so these are the two different systems. Okay, so the HIDS might use pattern matching and the observer. So these are the things that I'm going to talk about later, but they basically both work on the same way. Just one is focused on a host, and the other one is focused on the network segment in general. Okay, so how does IDS work? IDS looks for suspicious activities, look for anomalies. So it looks for two things. Some IDS systems look for all of them, look for the two of them. Some are designed to look for just one of them, which is what we call signature based and anomaly based. And these things can be looked at as a packet per packet or as a stream of packets. Right? So this is another differentiation. Um, the signature-based IDS look for certain signatures, certain patterns, and as I said, they can look at these on a packet by packet basis or as a stream. We'll call these stateful matching. The anomaly based, there are four different types: statistical anomaly, protocol anomaly, traffic anomaly, and rule or heuristic based anomalies. Okay, so what is signature? Just before we talk into signature based analysis. If you go back to the topic of malware and the topic of viruses, worms, etc., if we know those viruses, usually we, the people who are continuously fighting to detect or to discover viruses, remove them from systems, they will see the traffic as they will see the virus as a code, as a piece of code, the piece of code with instructions like any other application. What they do is try to discover a unique set of codes that identifies this virus. Right? So if I'm looking at any piece of code, I may see a set of instructions, set of codes that uniquely identify the virus or the worm or whatever malicious software is. So every time I see it, I say, okay, this is a virus. Right? Actually, from the other side, viruses try to mutate and change them. Some of the ways to avoid detection is to try to change the code so we will never see the signature. We will never know the signature. But there's always a battle between the hackers and the security people, and we try to find common signature of the virus. Once we know the common signature, what we can do is every time there is a packet passing through the IDS, we will look at the payload and try to see if this signature is within this payload. If we see it, well, we know that this is a virus, and we alert the administrator. So this is basically what we mean by signature-based. Of course, signature-based means that we already have seen the virus before, we already have analyzed it and discovered its pattern, and we saved the pattern, so we know it. This means that this kind of signature matching or signature-based analysis cannot be used for zero-day attack that I talked about earlier. Those are attacks that I've never seen before, right? But these can be used against known attacks, known viruses. The difference between the signature matching and the stateful matching is that the first one tried to look at each packet as an individual entity, so it looks at packet by packet, so it doesn't look at certain patterns or long-term patterns. While stateful matching improves upon that by looking at session, for example, or a stream of packets going to the same direction, and looks at the sequence and say, well, maybe the pattern itself can happen over multiple packets, not just one. So the pattern that I talked about, it's not just across one packet or contained in one packet, but across multiple packets. So it's part of it here and part of it here. So now we say these packets are containing virus. So as I said, the Pattern and stateful matching can detect only known attacks. They cannot detect attacks that are unknown before. So we need to continuously update the IDS by new signatures, continuously find new signature and teach the IDS about them so that they can be discovered. The other kind of IDS is the one that try to detect anomalies. So there are four. The statistical based methods, they try to develop baselines for the normal traffic volume, normal traffic activity. So they see the traffic, well, at 8 o'clock in the morning, the traffic at this level, 8 or 9 traffic at this level. So they build a baseline and they alert when they identify significant deviation from that baseline. We call them statistical because there are certain probabilities involved. So that you cannot just say if the traffic is normally 1 megabits per second and all of a sudden went to 1.1, so that's must be anomaly, because this could happen for normal reasons. But we develop or it has to detect anomalies within certain probabilities, right? And that's why it needs to develop this baseline over significantly long period of time. We're talking about maybe a week, 2, 3, or a month, right? So before we start seeing, before we develop an idea about what is actually normal behavior and what's not normal behavior. The other kind is traffic-based methods, which signals alert when they identify significant deviation from expected traffic levels. They look similar, but the thing that the difference is, let's say there's, as I mentioned before, there is usually SNMP traffic coming from a certain device which is used for network management. So SNMP traffic always coming from that device. And all of a sudden SNMP traffic goes beyond the normal volume, or it comes from a different server. Well, that's not normal, right? So that's unusual. Right? Another way to explain this is by seeing a lot of pings coming and scanning the entire network, pinging the entire network. So that's not normal behavior, or at least not normal every time. Maybe network management system is trying to discover discover if the networks are or devices are alive, but that happens within certain period of time, and maybe it has a certain characteristic. But if somebody is trying to hack into the network, maybe they do it at a different time of the day or from a different location. So all of these indicate something that's not normal. Another type of anomaly is change in the protocols themselves. ICMP has well-known options: echo reply, um, time expired or TTL expired, redirection. All of these are known. I may have said the wrong names there, but all of these are known options. If you see ICMP packet that doesn't have a known option, well, this must be really wrong, right? Maybe somebody is trying to actually deliver malicious code on top of or in an ICMP packet. Same thing with DNS. DNS has specific records, specific patterns, and people and hackers sometimes use unknown DNS options to carry attacks. The final one is rule-based methods, or as I said before, heuristic methods. This is where the administrators say, I'm going to give you a certain rule. If you see 3, 4 attempts to log in to a server and they fail, give me an alert. Right? if you see ICM packets coming at rapid speed, by default, ICMP packet may, if you send continuous ping from a device, they come every 30 seconds or so, right? If you see them coming every 10 seconds, this must be uh, abnormal and give me an alert. So you can develop a lot of uh, rule-based methods. You can develop a rule that says, if you see this particular keyword in the packet, give me an alert. You want to prevent certain data leaks. So if you see a pattern of credit card information which has a specific pattern, you give me an alert, right? So the rules could be developed, and a lot of IDS systems out there that actually they do this. They have a lot of rules, so you can look at the rules and you see a lot of them being developed to mitigate certain attacks or detect certain attacks. Um, so one of those um, examples that we'll talk about anomalies is the traffic or rate-based signatures. You can look at certain source and destination uh, information on the IP address, and then you see, well, if there's this traffic going into the server that I know it's a web server or email server, and the traffic exceeds normal level of threshold, then this could be an indication of an attack. Or if I see a lot of a device or multiple devices are sending SYN and then they're not finishing, they're not sending acknowledgement after that. Okay, so that's an indication of SYN flood attack. So these are traffic or rate-based signature, and then we see some attacks, we'll call them application signatures. These are some of the attacks we discussed them earlier that they target. They all basically trying to exploit some vulnerabilities in the software and use this vulnerability either to grab information or simply just um, stop the function from working, stop the server from working. So cross-site scripting, SQL injection, some known web exploits, some known attacks that uses OS commands, operating system commands, robots, spiders, scripts, Trojans, all of these server information disclosure, which comes from banners, right? So you log into a server and the banner appears. So some unintended information can be disclosed using the banners. Credit card leads, all of these things can be detected by IDS by looking at certain packets and certain behaviors. Right? And as I said, all of these can be created or detected by just putting rules. Okay. IDS can be deployed in many ways. This slide is just one way, so it's not the only way. But if I want to install the IDS in the maybe some of the riskiest path in the network, whereas there is a private network connecting to the internet, I want to look at the traffic coming in or sometimes going out to the internet. So I have three options. If I consider the general case where I have a border router or gateway router here and a firewall here, and the firewall will be filtering the traffic as we looked before. Firewalls will look at the traffic from the packet from the header perspective, right? So the layer 3 header, the layer 4 header IP or TCP or UDP in this case. So they will look at the traffic only using the packets. That's the packet filter firewall, right? Not the general term of next generation firewall or any of that. That's just limited to a packet filter firewall. So we'll put a firewall here, the router here, and if I want to put the IDS, then I can put it in theory in three places, either or after the border router, so it sits between the internet and the border router. So it sits really in the danger zone, right? So something outside of my network altogether, right? Or I put it between the router and the firewall, or finally behind the firewall. So there is a difference in each one of these scenarios. If I put it outside the network altogether, then what is the advantage of that? The advantage is the IDS will look at all the traffic coming to the uh, router, whether it's the router eventually routed inside or not. So it gives me a visibility of everything out there, jungle out there, whatever going in, going outside the network. I see here the internet, but it could be any outside network. It could be any network that I don't have a control over. Uh, and by putting the IDS here, sniffing the traffic at this path here, now I can see everything that's coming to the router, or even not coming to the router if I position the IDS in a specific way. The IDS in the middle here, it will look at the traffic that's decided by the router that it should go to the private network. So this is the router that should go to the private network, to my network. So it looks specifically at the traffic going in, but before it's being filtered by the firewall. So I can see all the traffic, whether it's filtered by the firewall or not. And finally, the IDS can be put here, which means that it will see the traffic after being filtered by the firewall. So any malicious traffic will be filtered, or any undesired traffic will be filtered by the firewall, and then whatever left will go through the IDS. Somebody would say, why would I put it behind the firewall? Did the firewall already filtered all the bad traffic? Well, consider the scenario where I am allowing traffic to a local web server, right? And I'm saying anything that comes from the outside is welcome to go to that web server, maybe in the DMZ instead of the private network. Regularly or typically it's supposed to be in the DMZ. So I'm allowing the traffic to go from the outside, to be initiated from the outside, from the internet, to that web server through or to port 80. That's allowed. That's okay. So the firewall will okay the traffic, will allow it to go to the web server in the DMZ. If I put the IDS to sniff the traffic that goes to the DMZ, it may discover something that the firewall cannot discover. It may discover the SYN attack. The firewall simply says, oh, okay, there's a TCP session that needs to be initiated. It's going to the web server. It looks okay based on the IP version 4 header and the TCP header. Okay, everything is okay. So let it go. But the IDS will see, okay, there are multiple SYN coming, but no acknowledgement, so they are still open. So this is an anomaly. I should be alerting the administrator. Another example is the firewall. Let's say the firewall say it's okay to ping the inside network. So ICMP echo is allowed. So the firewall will pass this traffic. The IDS behind the firewall will say, wait a minute, there are so many ICMP packets coming. Why there are so many of them? So maybe this is an anomaly. So it could be useful, or there is a good reason for putting the IDS behind a firewall. So each one of these location is a legitimate location to put the IDS, but again, IDS outside, it will be subject to all traffic, whether it's coming to the network or not. I may not be interested in looking at all traffic, so I may put it just behind the router. And here I'll look at the router that's being forwarded but not filtered yet. So I may see attacks before they start coming to the firewall. So I may see somebody who's trying to launch um, attack using a port number. The firewall may not allow it. So okay, so the firewall will allow only port 80 going to the web server, and I see a lot of traffic coming distant to port 8080. So the IDS will see it coming, but it's filtered here. So each one of these locations have an advantage and disadvantage. If money is not an issue, but money is always an issue, but if the cost is not an issue, I may have multiple of them. So what is the advantage of having multiple of them? I can use them for comparison. I can say, well, the IDS here sees certain traffic. The IDS at the back here doesn't see that traffic anymore. So this must be filtered by the firewall. So I know that the firewall is working. So I may have reasons to put the IDS in multiple points. And as I said before, this is just one example of putting an IDS in the path between the internet and the private network, or in the internet and the DMZ. But this is a general case of deployment, and there are two types of deployments in the IDS. I can put IDS in any place in the network, right? So we talked about firewalls. We put them in choke points between multiple networks of different risks. IDS can be also put in choke points between networks of different risks. And I can put them out of band or in line. So what is the difference here? Now let me go back to this picture here, and I mentioned at the top here that I can put traffic, I can put IDS in this location to sniff traffic in the segment. But we all know that Ethernet now is not a bus technology anymore. We we still use the bus symbol here to represent a LAN like Ethernet, but in practical terms, this is not practical, right? So there is no bus technology anymore, right? This is just a convention that we display a LAN as a bus. So how is LAN constructed? LAN is constructed using switches. That's the common way. And the switch will typically forward traffic based on flooding first and learning later. So host A wants to send traffic to host C. It will send a packet. The switch, over time, it will learn that the destination is always in this port, so it will forward traffic from one port to another by learning where it's located. So if I put my IDS here in this location, in this port, the IDS will never see the packets going back and forth between devices, so it's not going to look at anything. And I said that the IDS basically it's a sniffer. It needs to look at all the packets. So how do I implement the IDS? Well, the IDS needs to have, in this case, needs to use port mirroring, the technique in the switches. So we force the switch to copy every packet and forward it to the IDS. So every packets going between any two ports have to be copied and sent to the IDS. That's what we call out-of-band deployment, and it shows here the dashed line represent the connection where the traffic is copied, and the red line represents actually it's the other way around. The red line represents the copied traffic, and the dashed line represents the administrative interface. So like any other device, the administrator needs to connect to the device, so it needs a port, administration port. While the red cable here represents the port where the traffic is being mirrored and copied. The disadvantage of this technique is that there is always a limit to the bandwidth. So if each one of these ports here that you see has 1 gig bandwidth, and like any other switch port, the red cable also has 1 gig bandwidth. So now the bandwidth that's coming, or the traffic that's coming from all of these devices, will exceed the bandwidth of this. So there will be, at some point, the port will be dropping packets just because it cannot pass all the traffic to the IDS. It's too much. So in this case, either the IDS is connected to a port that has higher bandwidth, or we risk losing some traffic, some packets. Another disadvantage is the port mirroring does not copy everything. Right? So if the packet is received by the switch and the packet has errors, the switch will reject it, and it will not forward it. It will not forward the packet anywhere, and consequently also it's not going to be copied anywhere. So only the legitimate, correctly formatted packets will be forwarded. So that means that some of the packets that may indicate certain attacks are not being copied, and IDS doesn't see them. All right, so that's the out of band. The inline deployment will actually put the sensor in the path. So instead of seeing it here as being adjacent to the line, it's actually across the line. So the traffic will go to the IDS, and then the IDS will pass traffic to the switch and goes to the internal network. This is what we call inline, and the inline has an advantage. The advantage is that all traffic now has to go through the IDS, same as all traffic has to go to a firewall, right? But also means that the IDS will become a choke point, will become another source of delay in the network. The analyzing packets and trying to detect anomalies take time. So now the IDS will introduce an extra delay. The extra delay will impact the network, will impact the performance. Same thing we saw in firewalls. Put firewalls, well, the firewall will add another delay to the packets. Also, the IDS may be overwhelmed with packets, and it may fail in open fail, like instead of close fail. Close fail means the IDS will fail, no traffic will go. But if it fails open, means that, okay, the packets will come, the IDS cannot look at them, it will just pass them. It will pass them. So, okay, I cannot really process all of these overwhelming amount of packets, so I'm just going to let them go. Right? So that's another risk. Okay, so there is something that I didn't mention yet, which is another way where we can avoid having this scenario where the switch is has to mirror the traffic. We call this technique network tab. Network tabs, if you go search for them, network tabs are about devices that can be attached to a line, and they are powered, so they are not passive, they are powered. And as long as the power is on, every packet that comes through the wire, it will be passed to the IDS. Right? But they are designed so that if there is a power failure for that or damage to that power, to that particular tab, the traffic will go unaffected through. So they're not going to introduce any damage to the line itself. So tabs will copy everything, whether it's properly formatted packet or not, so everything will be passed, right? So that's another way to avoid put the network or put the IDS out of band, but at the same time will pass all the traffic to it. So these are deployment scenarios, and they can be deployed anywhere in the network, anywhere where there is a justification or the risk assessment say, well, it's a good idea to look at the traffic in this particular network. So, as this slide says, the greatest risk today comes from insider threats. So sometimes I want to put the IDS where the threat is. And I'll give you one example that maybe explains this. So in this particular example, I put this IDS in this network. Let's create a scenario where IDS, maybe it's justified. So I have a network that has a lot of sensors. I have temperature sensors, humidity sensors, all type of sensors, right? So we have this network, and those sensors eventually will be connected to a switch. Maybe they will connect to a wireless network first, right? And they will, or maybe directly, it depends on the situation. And the traffic from this network is not, there is no users here, there are just devices that collect information and send them somewhere, maybe a server here. Now I can put my IDS in the out-of-band deployment scenario. I can copy all the traffic to the IDS. So I'll be able to monitor all the traffic inside the network. The benefit of this IDS deployment scenario is that I can monitor this network. Instead, this network is an inside network, is an internal network, is not connected to the internet. But still, there is a risk. The risk is this could be one of the sensors replaced, and now a hacker can log in through the wireless and start scanning the network or attempting to hack the server. Or the attacker through the wireless network may try to send some malicious software that infiltrates these cameras, for example. So this is putting an IDS here will be able to look at all of these suspicious activities and say, okay, so this is not typical, this is not normal. Actually, this particular scenario gave rise to a new set of next generation firewalls, where the firewall itself, if you see it, you will see that it's actually designed to look like a switch. So you see the firewall with a lot of ports. Typically, the old generation firewalls, they have maybe 2, maybe 4 interfaces, ports, and that's it. New generation or next generation firewalls will have 24, 48 ports. And the reason behind that is they can actually be used instead of having an IDS like this. The firewall, the switch itself looks like a firewall, right? And looks like or acts like an IDS system. So the firewall is embedded in the switch, or the switch is or the firewall is the switch, right? So the one of the functions of the next generation firewall is an IDS, and it can monitor all the traffic passing through it. And it can do that at layer 2, not necessarily at layer 3. So it monitors all the traffic going through the firewall, which duplicates as a switch as well. Okay, so that is another type of deployment. In my opinion, the IDS is the next most important device in network security after the firewall, right? So because it has a lot of benefit and it covers some of the weak spots of firewalls. But they have challenges. Performance is one challenge. Performance, it does the IDS process packets and looks deeper into the packet, deeper than a typical packet filter firewall. So that means that it takes longer time. It looks for a huge set of rules sometimes, just looking at all of these rules and try to say if the packet matches one of these rules, it takes a long time. So there is a performance degradation when it comes to using a firewall, an IDS. Encryption. This is always a problem, whether it's a firewall or an IDS. If the traffic is encrypted, the IDS cannot look inside it. Especially if we're looking for patterns or signatures. It may look for volume, anomalies in volumes, but it cannot look for signatures, for example, because that requires that you have to look at the payload. Switched networks, again, I mentioned that all networks nowadays, they're not buses, they are actually a switch. So if you want to deploy them, you have to rely on port mirroring, like this case here, or so you cannot do this practically, you cannot do the top one. So you have to rely on port mirroring, or you have to actually put a firewall with 24, 48 ports, next generation firewall, I mean, instead of an actual switch. Well, suffice to say, next generation firewall that has an IDS function, it's not going to be cheap. So you have to choose between either use port mirroring and risk not seeing some of the traffic going on in the network, or go to an expensive solution. Another problem with the IDS is false positives. False positives is getting an alert where actually there is no reason for an alert. Again, as I said before, there are sometimes we rely on statistical analysis of the volume and say, oh, the traffic exceed normal. But that's probability. That's not always guaranteed that it's causing this. Actually, the traffic volume is increased because of an attack. It could be increased because of a legitimate reason. So false positives are common weakness in the IDS. Okay, so IDS alert, the pure IDS just alerts. It does not drop packets. Firewall drop packets. IDS, they don't. So if we move to the intrusion prevention system, now these systems can actually drop packets. So everything I talked about in the IDS, same with the IPS. Just the difference is they drop packets. But if you notice, I cannot drop packets if the IDS sensor is in a port mirror here or in a tab here. The traffic will still go inside, right? So to be able to drop packets, it has to be positioned where in line. So the deployment in this case has to be in line. I cannot drop packets if the IPS is connected out of band. So the only deployment way is to do this, do the inline. That raises a problem. The problem is, as I said before, there is the performance issues, and there are false positives. Switched network is not an issue here because we have to put the IPS in a choke point where there is only one link between two networks. But still, the processing time will delay processing of packets. Some packets are sensitive to delay. Video, VoIP, all of that, so it's sensitive to the delay. So the more I add, the more processing I add, the more impacted these protocols are. The other issue is false positives. So it's one thing to get an alert and go to find an alert and the alert is nothing, discover that the alert is nothing, is another. But it's another thing when every time there is a false positive, you lose connection, the IPS drops packets and say, okay, we dropped packets, even though there's no good reason for dropping packets. So IPS are, you can use them with caution here because they may drop packets and users will complain. And there were cases where actually IDS systems prevented the network from functioning because of a false alert. And the IT people scrambled and blamed it eventually on the IPS and said, okay, so the IPS dropped packet for no reason. So one way we can sort of prevent that from happening is by using IPS and IDS systems at the same time. Okay. So of course that's costly solution, but we can have IPS inline and IDS inline or maybe even out of band, but I can put them back to back this way. This could be a router or a firewall in the middle here. And design them so that if I'm doing a threshold, if I'm doing an alert or dropping packets based on threshold, I can make the IPS drop packet at higher threshold than the IDS alert. So how does that work? So I can explain this by going to a diagram here and see, let's say there is this traffic monitoring. The IDS and IPS both monitor traffic across the same path. This is the typical traffic going. And I put the IPS threshold here. And I put the IDS threshold here. What does that mean? It means that if there is an anomaly and an anomaly crosses the alert threshold, the IDS will tell me there is something going on and I get an alert, while the IDS still doesn't drop packets because the threshold has not been exceeded yet. Okay, so now it gives the administrator time to look at the traffic and say, is this a legitimate attack? If it's a legitimate attack, I can go back and reconfigure my IPS and change the threshold so that the threshold matches the IDS and starts dropping packets. If it's normal traffic and there's nothing to worry about, then now I can just acknowledge the alert, disable the alert, and no packets are being dropped. So now I don't annoy the users in the network. I don't drop any packets. I get an alert, I still get an alert, and I have a chance to look at the traffic, and I reduce the possibility of false positives here. So the IPS has to be inline. The IDS in this case can be inline, or it can be in um, connected to a port mirror, or sometimes called spanning port in some vendors. I mentioned firewall a lot, and what is the difference? So, and there is a common confusion usually because between the firewall and the IDS. And um, so let me clarify the difference. The firewall, when I say firewall, I mean a packet filter, stateful packet filter. Typically, the function of a firewall is to look at the packets, the packet header, layer 3, layer 4, and filters the packet based on the packet header content. And it doesn't look at the payload, it just looks at the header. And also, the firewall does not have the concept of statistical analysis or any of that, or patterns. It looks at the rules. The rules are specifically defined. If the packet matches this rule, the packet is either allowed or denied, and it goes one rule after another from the top down until it's either matching one of the packet or denied by default at the end. So the firewalls has specific rules to follow. The IDS, on the other hand, monitors traffic and spots patterns. So that goes beyond the headers. It goes sometimes into look at the volume, right? The firewall does not, if you allow TCP traffic to go through the firewall does not care about whether it's 1 megabits per second or 1 gigabits per second. You said that all TCP packet is allowed, it will allow all TCP packet. It doesn't care, right? IDS, on the other hand, you can develop a rule or that says if you exceed certain traffic bandwidth, start dropping packets or start alerting in the case of IDS. It can also look at some type of attack, known attack like SYN attack, and say, well, this packet SYN is coming from the same source, but there's no acknowledgement, so there must be some kind of a malicious activity here. So the IDS look at traffic, suspicious traffic, volume-wise, behavior-wise, signature-wise, all kind of anomalies. Something that's not normal. So you think of a firewall as a guard who looks at the ID of the people coming through the building to the door and say, "Are you?" or "Give me your ID." Looks at the ID. Okay, this guy or this person is allowed to go in. All right, so go in, right? Or this person is on some kind of blacklist. They're not allowed to go in, so we're not gonna let you in. That's the firewall. It's a guard, security guard. The IDS it looks like a camera, security camera, or multiple security cameras in the building, that after the person goes in, it starts looking at that person, monitors that person activity, and looks at and say, is he behaving normally? Why is he trying to open multiple doors instead of going to a certain office where he has a meeting, right? So it's something suspicious here going on. So this is the difference between firewall and IDS IPS systems, and close analogy, I hope, that explains the difference between the two. Okay, let's look at the second second system in our collection of systems and tools. It's a sandbox. So, what is the sandbox? A sandbox is a security mechanism that isolates running programs to mitigate system failures or stop software vulnerabilities from spreading. Remember back when I said there's the zero-day attacks, and these are the attacks that we haven't seen before, so we never got a chance to do anything about them. A sandbox is another tool in our toolbox that help with these kind of attacks. So we already talked about viruses. People analyze the viruses, create a signature for them, and say, well, here is, if you see the signature, this means that there's a virus and you can eliminate it. Again, we can, so if we design our IDS system or some kind of next generation firewall to look at the packets coming and look at um, and see the signature inside and say, okay, here's a signature. I'm going to drop this packet because I know for sure that it's a virus. Maybe not even firewall or IDS. Maybe I'm sending an email to the email server, and the email server analyzes all the attachments of the emails, and looks at the attachment and say, okay, there is signature of a virus in this attachment, so the email, I'm going to drop it. I'm not going to forward it to the user. It has a virus. You may also receive an email with multiple links and they look suspicious. So if the links are known to be links to malicious websites, though they may be blocked by the email system or by the IDS, it knows that this is a well-known malicious website. I'm just going to drop the email. All of this, we know what's good, right? Or we know what's bad, and we make a decision based on this knowledge. But there is also a gray area where I don't know, or I don't see a signature in this attachment. I don't see a specific signature, but it looks suspicious. This code, the attachment is supposed to be maybe a document, Word document, or maybe PDF, but this attachment is neither. It's something that I didn't see before. It's an extension that I don't know what it is, right? So it looks suspicious. Or this email has a lot of links. They're not um, malicious, so I don't know. They are not part of the malicious websites that I know. But why there is an email with a lot of links? That looks suspicious. So this is where the sandbox comes in handy. Uh, so we can send these applications, links, files to the sandbox. The sandbox is basically a well protected system that includes um, all the um, all the resources that it needs to run isolated from everything else, right? And this system will be able to open that attachment or run that application or visit that link and monitor the behavior. What happens next? And if something suspicious happens next, then we know that this is a malicious activity and we block the email or drop the packet or whatever. If not, then we let it go. Right? So this is what these two slides talk about. Sandbox is often used to execute untested or untrusted programs or code without risking them harming a host machine. And the sandbox typically provide tightly controlled set of resources. Think of a really tightly controlled virtual machine that you can, it has the same operating system that you need, but nothing can get out of it, right? So if I run an application inside it, it cannot get anywhere out. They can be able to detect known malware signatures, or the antivirus systems may be able to detect known malware signatures, but if something unknown before, the antivirus systems will not be able to detect it. So we may rely on the sandboxes to, let's test this in a secure environment to see if it's okay or not. Also, any suspicious links, any suspicious files can be opened safely inside the sandbox. Um, the sandbox itself can be a physical device. It depends really on the organization and how the size of the organization, how much investment we need to make in these devices. So it can be a physical device, in-premise device connected to the network. In-premise device allow us the highest performance, allow us the highest customization because it's in our location. It can act quickly to any um, traffic coming, so it's located, uh, and it has its own resources. It could be part of a unified threat management system or next generation firewall. So a lot of next generation firewalls include this sandbox. So it can be another um, another service that we can activate. So now it's the firewall itself is also a sandbox. It can be a virtual machine. Again, a virtual machine can be hosted locally, or it can be, um, and there are also sandboxes that are provided by by a company that just offer these services for a fee. Right? So it could be a cloud service from a service provider. In the latter case, uh, you remember the performance. So if I receive a suspicious email with a suspicious attachment, and I'm not sure, it looks suspicious, but the antivirus does not see any signature in it, and but it's not completely trusted. So it's neither. I cannot judge whether it's malicious because I don't see any signature. But again, it's not one of those files that I can let in because it has a unknown unknown signature, unknown extension, or or simply it doesn't meet my criteria. Right? So I may design a system that says any PDF larger than few kilobytes, maybe you have to check it out first. So you will send it to the sandbox. If the sandbox is local, this may take milliseconds, plus the amount of time that the sandbox needs to test. But if you send it to a cloud, then it's going to take maybe more than milliseconds to go to the cloud, be executed, run in the virtual in the environment in the cloud, and then come back with a decision. So every time you have a deployment in the cloud, you have to think about the performance impact, right, and the delay impact. So that a decision cannot be made whether the email or the packet can be passed to the internal network or not unless the decision is made. So it takes time. Okay. Speaking of emails, another tool that we're going to look at is the spam filter. So spam, as you know, is a form of annoying commercial advertisement that comes through the email. Um, there is an estimate a few years back that more than 95% of email messages sent worldwide is spam. Imagine how much spam. So if you're receiving 5 emails a day from legitimate sources, probably there are 95 other emails that came as spam, right? Um, Now you don't see them, right? Thanks to a spam filter. From the spamming from the spammer's point of view, this is nothing to them, right? So sending millions of emails, even if 1 in 1,000 reply, they're still making a profit. Somebody clicks on the link, finally believes the advertisement, and say, okay, let's try it. If 1 in 1,000 do this, they're still making money on a daily basis. So for them, it economically still good. For the rest is annoying. And spam, but beyond the annoyance, spam can also be a way to do more harm than just annoying people. They can be used to collect IP addresses, collect email addresses. You are sending a spam to somebody random. Maybe the spammers can generate random email address. They know, for example, the university has, or even Gmail has gmail.com. So they just put a random sequence of characters at the front of it and send the email to the university. And maybe somebody replies. If somebody replies, well, we know that there is an email or there is a person behind that email. So they can collect information and they can sell them to people who are actually trying to do more harm. Or the spammers can also use spam to deliver phishing attacks. You see a link, you click on the link, and the link will take you to somewhere where you download malicious software or fools you into entering sensitive information or all kind of things. So short uh, long story short, we don't want spam. So here, repeat of what I said, spam can be, that has serious effect. Lost productivity. I didn't talk about lost productivity, but if you have a spam and you want to go through the spam, just to make sure that there is legitimate email there. So if you have 10 emails coming to you and you click on each spam just to make sure that this is not legitimate and you keep deleting it. Oh, this is a spam. It's not legitimate. I'm going to delete it. And it will take you even a minute to read the spam to make sure that it's actually a spam. That means that you are wasting time instead of doing some actual work. You're losing time doing some just deleting spam. So that's another like reason for not wanting spam. All right, so what do? We do a spam filter. So how the spam filter works? Well, first of all, a spam filter usually is associated with email servers. So it could be a software by itself. Again, it depends on the organization and how much email we're receiving. So imagine a university has uh, tens of thousands of users at any given point in time, and they're all receiving email constantly. So it may need a specific piece of hardware that handle all that volume of spam. So it can be a independent product. It can be an add-on to an email server for a small organization, few emails. So I may just add it um, just to the email server itself. It could be also part of next generation firewall. So the firewall itself or the device that's called next generation firewalls has some spam filtering activity. All right. Um, so how does spam filter work? Spammers are known, or a lot of them are known. So we can simply create a blacklist that says any traffic, any email coming from this particular spammer, we just block it, right? So blacklisted, we blacklist those spammers. It's well known that some spam filters may let's say you are, uh, and it happens to researchers sometimes all the time. Researchers want to invite they researchers want to have a conference. They want to invite researchers from all over the world to attend this conference. So they send uh, a mass email to tens, hundreds of people inviting them to this conference. This could be confused as a spam. So, and you get blocked in the IP address where the spam comes from. It gets blocked, well, because a spam filter suspects. So sometimes blacklist they have a disadvantage, but if there are known spammers, then we can create a blacklist that says, well, this IP address is blocked. Get rid of it, right? Um, the blacklist can be downloaded to a spam filter, and in this case, well, it's static, unless somebody goes manually and um, add details to it. Some spam filters product, it comes with a subscription, so you get the spam filter and you get a subscription to the provider, to a provider that says, we you pay this amount of money and the blacklist will be updated regularly every day, every week, whatever. So these are real-time black hole lists where um, the actual list is maintained by third party, so you don't have to worry about it as an administrator. The flip side of this is a whitelist. So whitelist works by um, deny by or allow by exception. The blacklist would be allow by, an example of allow by default, deny by exception. So unless somebody isn't on the blacklist, everybody else will be allowed, but those on the blacklist will be denied. The whitelist works differently. The whitelist is allow by exception. Everybody else is denied. So unless you specify the sender, um, then it will be blocked automatically. So that's a problematic because I cannot possibly list all the people that are legitimate or all the IP addresses that are legitimate out there and put them in a whitelist. So that's a little bit maybe cumbersome unless I am working in a very, very secure environment and I'm allowing only few set of organizations or few set of sources to send me email. Right? Otherwise, it's probably not practical. Then there's the final one, which is the gray list. The gray list works by using a phenomena uh, known by spammers. Spammers don't waste time. They don't want to waste time. They want to send millions of emails per day, at least. And if I'm sending an email to a server, let's say I create a fake email, xy12 hash, or maybe not hash, af at university.com. And I don't really know if this is a legitimate email or not. I just created it randomly. I'm going to send it to the email server. The email server automatically rejects this. So using the gray list concept, the email server sees this email from this spammer. It rejects it automatically. Even if it doesn't know if it's a spammer, it just sees this for the first time, say, I'm going to reject it. It's coming from this source. I'm going to reject it. If he is a legitimate source, they will send the email back. They will send it back. Right? If it's a spammer, the spammer won't waste time. They will send an email. If the server rejects it, they won't try again. Why? Because they said, okay, I already generated this email randomly. And if the email server on the other side rejected it, then this means that it's not real email, so I'm going to move on. I'm not going to waste time. While a real person or a legitimate person, legitimate server in this case, not a person, but server, um, they will try again. They know that this email is legitimate and they will send. They get rejected, so they will send again. The second time the email server sees this email coming, they will say, okay, this person tried again, so I'm going to let them in. And I'm going to build my gray list. So next time I see the email from the same server again, I'm going to allow it. So the gray list is built dynamically. Somebody sends an email, drops first time. If they try again, I'll say most likely these are legitimate, so I'm gonna allow them. Right. Now this is similar to, if somebody calls you, you don't answer the phone. If they really want you, they will leave a message. Right? So that's how you differentiate between legitimate callers and spammers. Sometimes spammers leave message, but then you can hear the message and find out. All of these are list-based filtering criteria. Another filtering criteria is based on content. So now we don't filter based on where it's coming from, but based on the content itself. So the simplest thing is look for the words in the message itself. If I see specific word like sales or any word that I don't want it to come in, right? So associated with email, I may just block the email and say I'm rejecting it because it contains this message. Word-based are not accurate because there are ways for the word that I'm rejecting that to be in a legitimate email. So this is a weak way to do it. I could also do heuristic filters. Heuristic filters say it looks at certain criteria. So the email comes and say hi, but it doesn't say the recipient email. So it's not hi, John. It's just hi, and there are lots of links in it. And maybe it talks about sales and talks about we offer you something, and then there is no signature at the end, so there is no name of a person or a tag that says this is the company where it's coming from. So kind of when you look at this and say, well, this is suspicious, this must be a spam, so you reject it. The third type, Bayesian filters. These are employ probability and statistics to determine which messages are legitimate and which are spam. And sometimes they learn by how the user flagged the email. So if the user look at the email and delete it or move it to the spam folder, say this is spam, then the filter will learn, okay, so this user deleted this email, so I'm gonna learn that next time um, uh, the email coming from this source, I'm gonna treat it as spam as well. So it looks at laws of or uses probabilities to detect spams. Another security technique or another security tool is what's called Security Information and Event Management System. A few years back, this kind of system was hyped so much that everybody was talking about it as the best solution in security. It is a powerful mechanism, a powerful tool, but maybe is not as hyped, as not as or is not as good as people hype it, right? Uh, so what is it exactly? The security information and event management system is a product that is a combination of two techniques prior to it. One is something called security event management, which is the segment of security management that deals with real-time monitoring, correlation of events, notifications, and console views. And the second part is the security information management, refers to long-term storage, analysis, manipulation, and reporting of log data and security records. So these two systems, you combine them together, you get something it's called SIM, or Security Information Management Systems. You can see here that there is a common thing. Monitoring, correlation of events, notifications, logs, storage, analysis. So these are the things that we need to look at. The main thing that the SIM does is do a real-time analysis of the security alerts. And I may kind of dispute the real-time thing here. Maybe it's not real-time, but close to real-time, and I'll explain why. Anyways, I'll explain the components of SIM, and then we'll see what each one of these components deal with. So it is known in network management that and in security as well, that systems can generate logs. And we talked in access controls about accountability, and accountability through generating logs. So in access controls, we have the accountability part of access controls, and we are supposed to monitor the behavior of the users. Even if they are authorized to do something, we still need to monitor their behavior by logging their behavior, and then later we subject those logs to scrutiny, to analysis, and see if the people actually, or the logs actually, don't indicate any problem. So that's one part that's related to security and access control. But I can also have devices in general, whether it's a switch, whether it's a firewall, whether it's a server, you name it, any device generates logs. And the logs are generated every time there is an event. We can define what the event means. So if the switch, if a switch port turns off, I can send a log message that says the switch port is off, is disabled. If a firewall drops a packet, I can also send a log message that says packet is dropped. If a server receives a login request, I can send a log message that says a login attempt has been made. So all of these logs, normally, they will go to a log server, and they are kept. Now, sending logs is half of the story. The other half is somebody has to come later and look at those logs. So there are a lot of log analysis software out there that will take these logs, analyze the means, generate statistics out of them, looking for some type of anomalies, looking for some kind of behavior. So anomaly, for example, if the server is subjected to 3 attempts of log and each attempt failed, and the final 4th attempt was accepted, so all of these attempts are logged. Somebody will look at them and say, why there are three log attempts and failed and fourth? Maybe somebody was trying to hack. If a port failed uh, and then came back on again, so went off and then went on again, a switch port, well, why this happened? Maybe somebody unplugged the device, unplugged another device. A packet was dropped by the firewall. Well, okay, so it dropped because it matched a certain rule. All right, so one packet dropped, fine. 10 packets dropped. Okay, so we have an attack. So all of this can be done by analyzing. If you and this is what basically the SIM does. It collects logs from different sources and look at them and analyze them and discover if there are security attacks, right? That's why I'm kind of hesitant to say this is a real time, because usually, well, something happens and then the log is sent and then there is analysis. So that's maybe, or we don't know if the log analysis happens a minute later or an hour later. So it could be not near real time, but not necessarily real time. The firewall will see a packet, will drop it immediately. So that's a real time event. But the log may be analyzed later. So I'm hesitant to call it real time here. Um, one of the issues of the log is that uh, even if all your devices are coming from the same vendor, it is unlikely that they all follow the same format. But imagine a server will be produced by a certain vendor, so the server will have a certain format of the logs. And the common protocol usually is a syslog that's used for this, but we can have other notifications coming from other sources as well. SNMP can send traps, and netconf can send notifications. So we have other sources of notifications coming, but all of these, they have different formats. So the first hurdle, obstacle, is these are different formats. And I cannot analyze something that has different formats. I need to have all of them in one format. So the first problem that faces SIM is logging. And how do I do log? Right. Um, so the SIM must be able to interpret the log data, and this requires that the SIM parse all these logs of different formats and extract the information and reformat them so it can perform analysis. So this means that the SIM has to know the format of the log coming from the server, knows the format that's coming from a switch, different kind of server, laptop, etc., and convert them. Which means that the SIM vendor has to actually have a relationship with all of these other vendors so that it can understand their formatting and then convert it to something that's unique or something that's, generic. So some log records store data in specific formats like username, start with the position 10, the maximum length is 30 characters and so on. But some of them, they organize them in a key, a value. So the username equal some name, IP address equal. So you don't really know. These are just two examples. So you don't know what the format is. So you need to convert everything into a generic format that the SIM can use. Okay, so that's one issue. The other issue is how to get the logs themselves. So there are three different ways, or two or three. So the device can send push log records. So these are the syslog works this way. So syslog protocol will send a log message every time there's an event happening. So that's generated by by the device, and will send a log to configured log server. That's a push. Um, Sometimes these happen in real time, so as soon as possible. Sometimes, for efficiency reasons, the push happen uh, periodically, not as soon as it happens, but after or every 5 minutes, let's say. So we send them in patches instead of sending them in real time. So the router will save all the logs and then will send a group of them every hour. So that goes back to the real time issue here, that if it may not be actual real time. Another way for the SIM to collect information is by doing pull. Some way to get the logs is by actually logging into the device, the remote device, and taking the logs from that device. So um, this means that the SIM has a way to log into that device, means that we need to have a mechanism to log. So username and password usually don't work for devices, so we need to have a digital certificate or something like that we can, or a ticket that we can use, or the SIM can use to grab this information. So two methods of push and one method of pull. Okay, another thing that SIM always works by making sure that logs come from different sources. So SIM by itself is not going to work. You cannot just install SIM and say, okay, so it's going to protect my network. No, you have to configure all of the other devices or the devices that you really worry about to send logs. So this is one of the things that are different from any other devices that we have seen so far, is that those devices, they don't need the collaboration of all the other devices in the network. They need to just be put in a specific location, deployed in a specific location, in a specific way in the network. You cannot just buy SIM and install it. You need to configure other devices to send logs to that SIM. Okay, so let's assume that everything is configured properly. There are logs and all of that. We come to the second component, which is the correlation. Correlation is where the SIM goes into the records and look for specific patterns. Okay, so a log sees, as I said before, a user trying to log in multiple times and fails. So that's maybe a suspicious activities. But that's just one device. Let's combine this with uh, a user logs into a server after 3 or 4 attempts manage to log successfully, and then there is a surge in bandwidth detected by the IDS, and we detect also that there is detection of credit card information being in the packets, being in the data. All right, so what does that tell me? It tells me there's somebody who hacked into a system and stole credit card information, right? Or if there's no credit card information, but there's a large volume of or files that being downloaded, okay, we'll see that those files, maybe somebody is trying to steal trade secrets from a company. So all of this is correlated among or across multiple devices, so we can see a picture, right? So this happened and this happened and this happened, then okay, so we see a sequence of events. So the SIM will alert us that this happened. SIM can be used for forensic analysis. Let's say an attack happened and gone and everything, but we can go to the SIM and say we piece together a sequence of events to see what happened exactly. So after after the fact. SIM can also be programmed to have a specific correlations. And a lot of SIM products right now, they're not really intelligent that much. You have to program them. They probably come with pre-programmed correlations, but you can program them as well. So correlation here, you can say generate an alert after after three failed attempts to a server, right? So you can program it to do this way. So now, what happened? What happens in this case? The SIM will look at the logs and see three logs that say failed attempt, failed attempt, failed attempt. So it sends an alert. Right. So here, SIM alerts on multiple failed login attempts following by successful login from the same IP. That's maybe a trigger or something. There's a abnormal data transfer from a web server to external IP. So these are the things that can happen, and we can use it, as I said, to enhance investigation. The correlation can be done in many smart ways. Some vendors claim that there's an AI that discover things and all of that. So correlation is one thing. The alerting is the third component. So we need to alert. We need to send somebody a notification. That notification can happen as an email, SMS, whatever. And the alert also can be based on certain threshold. Right? So you see all of these things happening multiple times. If things happen more than certain amount of time, okay, send a message. One failed attempt may not generate an alert. Somebody simply failed to remember the password, so the login failed at the first time. But if you see multiple, then okay, maybe I'll send an alert. The final thing is the reporting, the final component. So we see here with the system can enhance investigation, can cross-reference multiple logs to indicate something malicious happening. So you can generate a report to the administrator, to the senior management, say, okay, within the last month we have been subject to multiple attacks. Maybe the attacks were prevented by firewall or IDS or whatever systems, but the logs are generated that shows we are being subject to these attacks continuously. So maybe we need to do something about them, or maybe we'll take this to prosecute the attacker if somebody is continuously trying to attack us. So maybe we'll go after them legally, or there are a lot of failed attempts by this particular user to come. So maybe this person needs to be trained. This employee needs to be retrained to use the system. So we can use this reporting to allow the administrators to have a view. Sometimes the word dashboard is being used. Generally a view of what's going on in the network. SIM can be deployed as on-premise or in the cloud. As I said before, on-premise allows you to have a piece of hardware or a virtual machine that does all of these things. You pay for it upfront and you need to maintain it, and maybe after a few years you need to upgrade it. It's secured. The performance will be the highest because it's in the local network. But if you misestimate the capacity, it may be too many logs, for example, to handle. So that will be hard for you to upgrade later. So you are stuck with this. But the cloud-based, on the other hand, there is a potential performance issue, you're going to send the log somewhere else, right? So you may, if you are looking for some kind of real time or near real time information, this may be delayed. But there is also operational cost. So you don't pay upfront, but you pay monthly. So that means that there is operational expenses going on. Some organizations prefer just capital expenses, which means pay something and that's it. Or some organizations will prefer to have operational expenses, so pay over time. And one of the cloud attractiveness is coming from the operational expenses. So instead of buying something that you need to power and maintain and have a space for, just um, put it as an expense in the cloud and upgrade it when you need to, as at any time you want. The final system that we're going to talk about today is the identity management system. So identity management systems, will see it in many occasions in this course. We already have seen um, identity management systems, sort of, in when we talked about um, access control mechanisms. So we talked about identity and we talked about verifying identity, right? So identity management system does keep tracks of the identities of employees and allow the administrators to verify them. So sometimes they are called IAM or AMI, I think. I got this acronym wrong, maybe. But the additional A is for access. So identity and access management, IAM. So this, you may see this acronym in these slides or in other slides. So what are the identity management systems? They manage information about the identity of users and control access to assets. So they are good for access management and they provide centralized access management. The IMS store information in all aspects of identity management infrastructure and use this information to provide authentication, authorization, and access, right? So we'll talk about the functions of the identity management system. Then we'll go a little bit further and talk about components. So this is a little bit elaborate. So the first component here, information storage. Then we have authentication, authorization, registration and enrollment, password management, and administration. So let's take a look at each one of them. I already mentioned the advantages. So there are centralized management of all of the users. So the users in the case of in the identity management systems, they don't necessarily include only the employees or only the members of the organization. Sometimes they are unknown or new users. Imagine you are logging in to something like an online retailer, right? So you need, so from the retailer perspective, they don't know you. You are a new user. From your perspective, you need to create an account. You need to put your information so that you can revisit that online retailer multiple times, purchase something, and all of that. So the IMS will handle all of this, right? So we'll handle everything. And they can be used also as a single sign-on. We talked about single sign-on before. So these are the advantage. The users require a login for every application, which is in turn burdens the user. So if all of this is managed by the IMS, that means one login for everything. So that's the concept of single sign-on. Managing all of these, managing from the administrator point of view is also a problem. So centralizing this management and automating some of this, as we will see later, automating some of the functions of uh, of the registration, all of that will remove that task from being done manually by the administrator. All right, so uh, information storage can. This is all of the information that can be stored in the identity management systems, the applications for the business, the databases, devices, facilities, groups of people, operating systems, the people themselves, any policies, any rules. So all of this can be, this is a huge information that's managed by the identity management systems. And by the way, as I said, we will see these repeated multiple times, the mention of the IMS or the IAM. If we go back to the cloud, a lot of this, um, a lot of the cloud functions are dependent on identity management systems. Okay, so let's see one of the functions of identity management systems. A user initiates a request for access to a resource, so that request will be issued to the IMS. The identity management first authenticates the user. So authenticating means verifying the identity by asking for credentials. So credentials here, username, password, digital certificate, smart card, or biometric data, all of any or some of these, combinations of these. After successful authentication, the identity management system authorizes the appropriate amount of access based on the user identity and attributes. And then every time the user will try to access another thing, so that will go through the identity management system, which means that the user will not be asked to log in multiple times for different services. So this is what we talked about as a single sign-on in previous lecture. As I mentioned, sometimes the user is not known to the organization in advance. And sometimes the user is known to the organization. So if they are an employee, so the user is known. If they are not, a customer wants to purchase something. So now the user has to do a registration process. So the external user will register by, you go to provide your username, you select a password, you may be asked for your physical address, you may be asked for your email address, maybe credit card information. So all of this is part of the registration and enrollment. Internal users usually registered by the HR or registered by the administrator. So you get hired by a company, you probably, the HR will get your information and they will register you before your first day of starting day. Everything will be set up for you. Another part of the identity management system is password management. So what I mean by that, um, first there's a policy for passwords, so 8 characters, capital and small, and etc., etc. So that's managed by the password management. Then maybe you need to be periodically asked to rechange the password. So again, you can go and change the password every 6 months or so. You forgot your password, so you call the administrators. The administrators will reset the password for you or give you a random password that's valid for 24 hours or so. So that's all part of password management. Auditing is another part where the system can be checked to see that is the user has the right privilege. So this is a user that registered or enrolled, and is it, do we have the most accurate information about them, right? It has been 2 years. Are they still within the same address? Do they need to change their password? Do they need to update their credit card information? So probably general along these general lines. Some of these services can be self-service, so you may be asked to do this periodically by yourself, or you may go and change your username and password, or email, or any piece of information about you by yourself without going to administrator. So all of this is part of uh, password or account management. It's probably account management in general would be the term. The administrator can be centralized or can be delegated. So a smaller or reasonably small organization or reasonably big organization may have one single administrator that handles all of this. So the administrators will do all of these IDS uh, processes in a centralized way. A big university, a big they have multiple campuses all over the country or multiple places in the country. Let's say they don't want to handle all of this in one centralized location, so they go to delegated administration. So what does that mean is that every campus will have their own IT department, and that IT department will deal with the students or employees in that campus. So they will handle all of this locally. So the administrators can manage some identities, some employees, only students who registered and study in that campus that will be managed by these. But they may not be able to do structural changes to the whole administration of the IDS. So that will be still centralized uh, by the central ITS, Central Information Technology Systems, right? So this may be a way of distributed the management, but keeping something centralized. Okay, so now we're going to talk about certain components. So the infrastructure will include, we'll learn about authoritative sources, directory components, administration, and so on. I'll try to draw this at the end, but if we'll see if we can draw it. If I can remember to put all of this in one drawing. So let's start with the authoritative sources. What does that mean? Well, if I want to talk about the identity of the user, right? So we want to do authentication. So, and we want to give the user identity, and then later we want to verify this identity. We need to have to start with a solid ground. We need to start from a solid ground. How do I know that this person is actually who they claim to be? The name, their address, their. So we need to start from somewhere that is we trust. So in the case of employees in a company, so the employees of the company, we will go to the HR, the people who hire them, human resources, say, well, you hired this person, so you must have solid information about who they are. You know that they graduated from this university, they have this license number, that you have seen their identity or driver's license, So you have seen all of this information. So that will be considered um, authoritative source. So the single point of truth or single source of truth, as they say. That's what we will trust. We will start from there. We will get the identity of the user from that point, right? So that's the what we call authoritative source, something we trust. The directory component, we talked about LDAP, which is a well-known open source software for directory management. So the directory component stores the identity, uh, stores policies, stores user credentials, and also provides some kind of logical structure to the resources. So it can allocate resources based, or it can organize the employees as uh, by department, by seniority level, by roles. It can organize them in different ways, and it can be used to manage all of this hierarchy and structure. So now we can use the directory to say, well, this employee belongs to this group of people, so they have access to these resources. The term that LDAP and other systems use is namespace. So the schema is the structure, namespace is the the resources that, or some of the resources that they can access. The directory integration component is it facilitates synchronizing changes between the directory and the identity stores and transferring information between the two of them. So again, if I want to try to um, maybe draw a diagram of this, I don't have a slide for this particular because I'm not sure how the system is organized, but I imagine that there will be a source, that's the trusted source that coming the HR, whether it's a physical database or I mean a computer database or something like that, digital database I should say, or a paper database. So it could be just a file for an employee that has all the information about them. So this file, or the content of this file, is translated to the directory. Something like LDAP. So that's the directory, that's the authoritative sources. So the authoritative source is here, and the directory is here, and then we have the synchronization. So this could be logically, I'm not drawing physical connections here, but logical connections. So the authoritative or um, sources connect to the directory components using this integration component. Uh, so it manages to do the syncing. So you don't expect that people from the IT doing this every minute. So, oh, is there any change? Is there any change? So there must be some kind of a system that does directory integration. If I use the acronym correctly, or component, so C instead of S. So it's synchronized between the two. So every time there is a change in one in the HR, it will be reflected in the directory. Then there's the provisioning component. So what is that? That's whatever part of the software that allows the administrator to add users, change users, and eventually deprovision, which is removing users. So you create an account. Well, that's provisioning. So you create an account for a new user. So that's a provisioning with certain amount of access, what this user can do and what cannot do. Um, so you can do all of this in the provisioning, and then eventually all accounts, people retire, people leave the company, people disable their accounts if they are accessing an online retailer, for example. Uh, so lots of reasons for the account not to exist anymore. So that means that we eventually need to delete this account. So this provisioning can be done by the administrator, or it can be done by the external user um, in the case of self-serve system. Okay, access control. So this provides management for authentication authorization methods based on role-based access control policies. So again, part of this, maybe during the provisioning, you will need to establish, or actually in general terms, not necessarily provisioning an account, but in general terms, you need to remember when we talked about role-based access, we said that access controls can be established or can be created based on roles, based on, okay, the CEO can do this, the IT department employee can do this, the accounting department can do this, without actually specific names. So you can have this being designed and built without specific users mentioned. When the provisioning happen, uh, the administrator will say, well, this user is part of the IT department. So automatically they will get the access or the authentication and authorization associated with the IT department. Anything that the IT department employee can do, that user who just been registered can also do. Uh, the administration components, this is the refers to the overall administration of the IDS system, right? Um, you want to have the administrators doing different tasks. So every administrator will have a specific task. If you want to delegate the tasks among multiple departments or multiple administrators, so you go and say, well, this administrator can do this campus, this administrator can do this campus, and so on. So you can, this is the part where you control the administrators, or you have accounts for the administrators themselves rather than the general users. Uh, this is a generalized application interface component. This is how the system looks, right? So the uh, the system can be somewhere in the cloud. So how do you interact with the system in the cloud? Probably through a web browser, right? So you may access through an app. So this is, generally speaking, refers to how you interact with the system. It's either allows developers to interact with the identity management system without having to interface directly with vendor-specific application interfaces. The directory integration interface facilitates the one-way data flow. Okay, so I'm gonna let you read this, pause and read if you want to. But the idea is you can integrate this either by logging in and entering information and having an interface, or you can log in, or you can maybe upload files using some kind of a markup language. You can maybe use API to connect another software to this identity management system. So we'll put all of this under general application interfaces component. And it also, remember, we need to control access to this particular system, right? So this particular system, IDS, controls access to everything else, but how about itself? So we need to probably control access to it as well. As usual, the now I mentioned the IAM, which is Identity and Access Management Systems. So it's the same as the IMS. The names can be used interchangeably. Um, I think the IAM is more common. So anyway, so the deployment can be on premise, which is hardware or a virtual machine located locally, or it can be in the cloud. And there are a lot of cloud options out there that if you Google them, you'll see a lot of IAM cloud options, especially when you are actually trying to deploy any services in the cloud itself. So you're guaranteed that you're going to be using um, identity and access management systems that also in the cloud. Okay, so that concludes our lecture today. Thank you very much for listening, and we'll meet in another recording.